Alright, let's start next round. I think I try to do 3 or 4 each round, or maybe 5, and then take a break, come back until I finish. Given an integer array nums, find a contiguous non-empty subarray within the array that has the largest product and return the product. Test cases are generated so that the answer will fit in a 32-bit integer. A subarray is a contiguous subsequence of the array. What's largest product? These ones feels like it should be easier than the previous ones. Maybe. So can't I get the multiplication of each one? I suspect this approach is not going to work because it can have different... I can multiply different numbers in the array. So again, it's the same thing, same pattern, but it's still having trouble coming up with the solution myself. I think it's probably because I'm going too fast through them at a time, and I'm not spending enough time reviewing the solutions of the other ones to really understand the thinking behind it. But that's fine, I think, because that's the first part that I'm doing this. The first phase, let's say. And the next phase, I think I'm gonna... The next phase, I think, is the phase that I'm gonna become actually better at solving each problem. Because this phase is more about understanding the principles behind them. And the next phase is really knowing how to apply them, so... doing them until I'm able to solve it. So I think I should have some sort of memorization here, and then it's the same thing pretty much from the other problems. You have a memorization, and then you have the tree, which is the possibilities of each one. So each number is going to be multiplied by another number, and then you have to memorize, so you simplify and you don't do redundant multiplications again once you reach the... So for example, if I'm at 2 and I multiply by -2, then once I get to -2, I don't want to multiply by 2 again because I already did. So maybe I should create a set here. But again, the tricky thing is how to create the tree, because... Well, I guess for each item in the list, I can add the value, and then I can multiply the key with the value pair. I can get the key value pair multiplication at the end. So maybe that's a way, but it's probably not the best. So I can make like this. And I'm not sure if you need recursion for this. That's another thing that I have a difficult time with, is understanding when I should and when I shouldn't use the recursion. Because recursion and looping is really similar, it's pretty much the same thing. But in some situations, it seems to be better to use the recursion, and on other ones, it seems to be better to loop. And it's kind of hard to figure out I still think I'm not able to capture the distinction there from both of them. Yeah, but if I make one key for each value in the list, then I'm repeating the elements again. It defeats the point of having the dictionary. So maybe I should do the thing again, or if num psi nothing then I make num psi equals equals num psi. The thing is that on this one, I'm not necessarily trying to build the tree, I think, because each one has only one possibility, so one decision. So I'm not trying to build the tree as I go through the first list. That's the difference. So maybe again I should go bottom up and figure out the maximum. So pretty much similar to the previous one, but instead of using minimum, using maximum. So maybe scratch this. Oh, I think the brute force approach, I can probably do it. Would be like this. And then total equals num psi times num j. Or actually, I think I have to put it on the same line. So it'll be the maximum or total or this. And then m dot appends total. Or m dot append I and j, I think. Oh, so we should return the product. I think this probably works. From total. But obviously it's trash, I think, even if it works. Uh, well, isn't 12 here? Why is it saying 6? Oh, so it has to be connected. Oh no. That'd be true because it's not a subarray. Okay, so it has to be connected. So it's even easier. But it can't be this easy. -7. Oh, it's because I'm making it -8 and then summing. So I should be equal here as well. What the fuck? Oh, it's because I'm getting the other one. Oh, so here should be max. Total. And this. Maybe I don't need this condition here. Obviously, I could test if there's a negative value in the surroundings. So either I or I -1 and that kind of stuff, but maybe it's unnecessary. I'm obviously missing something because it can't be this easy. I don't understand why this is true. Isn't it supposed to be the product? What? I don't get that at all. Because it can't be the product with the number itself, and if it has 2 and 0, then 2 times 0 should be 0. It doesn't make any sense. This test case here. I wonder how many I'm passing. I'm still failing a lot as well. So I'm probably misunderstanding the question. It's really weird the way that it is phrased there. I guess the issue I have is I don't understand what they mean by subarray. Because this doesn't make any sense to me. Contiguous non-empty array. Non-empty subarray within the array that has largest product. And return the product. A subarray is a contiguous subsequence of the array. Yeah, to be honest, I really don't like the way that they did this question here. It's just kind of difficult to understand what they mean exactly. I think I'm getting it right, what they mean, but if that clearly not because of the task case, because if it is what I was thinking, then it doesn't make any sense there. Because I'm thinking I should find the set of true numbers, so true neighbors that give the highest product from the array. And because of this, they have to be connected to each other. So, oh, so maybe also is not limited to true. I think I get it now. The part that I'm getting incorrect is that it can be any size of the array. It doesn't necessarily need to be the true. That's why that one's failing. Because it should be an array with one size. The only condition is that it can't be the numbers can't be split by the other numbers. I think I get it now. Yeah, now I understand. So it's a much harder problem if you think about it that way. No, but can't I use just two pointers as well? The sliding window technique. No, but again, that's the same thing. I guess I understand now why this is on dynamic programming. Because you can't really. And it's also the same pattern of the way that I'm thinking about it. I always think about the sliding window. And the difference is you need to test all the combinations, not just one. So sliding window is not that good. So maybe you need to create the decision tree for each number. Because as you move through that number, and you should loop through, should have a nested loop. As you move through one number, you should multiply and increase. So if the new total is lower than the other one, then you stop. So maybe this should be like this. So here I'm gonna put current actually, current and then total. And then I need two pointers, I think. Or I need a nested for loop. At least the easiest way I can think about it. Okay, so I'm gonna look at the solution. But what I was gonna do is create a nested for loop, and then for each number in the outer loop, I keep looping inside of the inner loop until the sum of the current one, the product of the current one, is lower than this one. So is higher than this one. The moment that is lower, then I just stop. So I keep increasing until it gets, yeah. But I'm not sure if the logic would work. And then I would append the result into this object here.
Hey everyone, welcome back, and let's write some more neat code today. Let's look at maximum product subarray. And this is actually a dynamic programming problem, and I'm going to show you how to solve this problem easily. So we're given an integer array of numbers, and we want to find the contiguous subarray that contains at least one number and has the largest product. So in this case, we have a 2, a 3, a -2, and a 4, and the largest continuous product we can make is 2 and 3 because 2 times 3 is 6. That is the largest product. We can't really make it bigger because there's a -2. If we multiply this by -2, it's going to be -12. That's not bigger than 6. So what's like your first idea how to solve this problem? Maybe brute force, right? Is there a brute force solution to this? Well, we want to find a subarray, right? So why don't we just try every single subarray? So let's say all subarrays starting at 2. We got 1 subarray, 2 subarrays, 3, 4, right? And for each of these, let's just calculate the product, right? Like the first one is 2, the next one is 2 times 3, the next one is 2 times 3 times -2, the last one is 2 times 3 times -2 times 4. And we end up saying that so far the biggest is this, but we're technically not done yet. All of these subarrays contain 2. So now let's look at all subarrays containing 3. So we got 1, right? Just 3. Then we got 3 times -2. Then we got 3 times -2 times 4. And basically we repeat this process. Now you can tell that this is not super efficient. The time complexity is big O n squared. For each of these numbers, we're going to end up having n subarrays, and we see that the total number of elements we have is also n, right? It's n elements in the array, so we're going to get n times n is n squared. So my question is, can we do better? And how can we do better? Maybe there's some patterns to this problem that we can use to our advantage to find a better solution than n squared. So let's look at one example. Do you notice anything about this subarray? Well, all elements are positive. So what does that end up doing? Like this is all positive. So we got a 1, okay? And next we want to check this subarray, okay, multiply it by 2. We want to go even farther, check the 3, okay, multiply it by 3. And what if we kept having positive elements? 4, 5, multiply by 4, multiply by 5. Do you notice something? Up until this point, our product is going to be a 1. Up until this point, it's going to be a 2. Up until this point, it's going to be a 6. Up until this point, it's going to be a 24. Up until this point, it's going to be 120. If we have positive numbers, no matter what happens, they're going to keep increasing, right? So this is the simple case. If we get all positive numbers, then our product is always going to be increasing. So now let's actually look at the opposite scenario. What if we had all negative numbers? Because all positives is easy. You just multiply all of them, you get the max product. But with negative numbers, it's a lot more tricky. So let's look at the first number. So up until here, the max product is just -1. And then we add, what's going to happen if we had another element over here? Actually a subarray that has a better solution. If you just take these two numbers, -2 times -3, we get a +6. So why did we get a -6 over here? How can we find the real maximum, which is +6? So even though we're looking for the max product subarray, we're actually also going to need to keep track of the minimum as well. And I'm going to show you why. So first, do you at least agree with me that if we want to find the max product array subarray of this, of the entire thing, it might be helpful for us to at least solve the sub problem, which is the max product subarray of just the first two elements first, and then use that to get the entire one. Okay, that makes sense. We know that the max product subarray of this is 2. Now, if we had a +3 over here, then we would say, okay, if I can get the max subarray of the first two elements and multiply it by 3, I'm going to get 2 times 3. It works when these are positive numbers, but we actually have a -3 over here. So I'm going to say, get the max product subarray, which is +2, but let's also get the minimum product subarray of these two as well. And what do we know about the minimum? What's the minimum product subarray of these two? It's going to be -2. So I'm going to keep track of both positive and negative. So we have a +2 and a -2. We keep the max and we keep the minimum. So now when we want to compute the max product subarray, when we include this 3, then we can compute that. We can compute that using both of these values. So we know that when we take the maximum, 2, we get -3 times 2, which is -6. And we know when we take the minimum, we get -3 times -2, and that gives us a result of +6. So we know the maximum is +6 and the minimum is -6. So we take +6 and put it over here, and we can take -6 and put it over here. And hypothetically, maybe we get another element, and this time whether it's positive or negative, right? So in this case, let's say it's -4, we will be able to find the solution because the minimum, or rather we're looking for the max product subarray, and we know if we take -4, multiply it by the current minimum, which is a negative number, -6, we will end up getting 24, which is what we're looking for. But if you reverse it, what if we had a +4 here instead? Well, in that case, we can say, okay, +4 multiplied by our maximum, right? Our maximum, which is +6. So 4 times +6, we get 24. We still get it, right? So this, if we maintain the maximum and the minimum, we have all the information we need as we continue to add more elements to our array. So now let's just look at one edge case. So we're talking about positive numbers and negative numbers, but we know that one last edge case exists, the dreaded 0 value, right? So what if we had a 0 value and then maybe some other numbers, 3, 5? Our 0 is going to kind of kill us, right? It's going to kill our streak. Like, look what's going to happen to our min and max. If we take 6 multiplied by 0, we get 0. If we take -6 multiplied by 0, we get 0 again, right? X times 0 equals 0. And then if we try taking this 0 and making it a product of maybe 3 and 5, it's going to continue being 0, right? Because any number times 0 is going to be 0. So I'm going to decide to handle this in a different way. So anytime we get a 0 value, I'm going to reset our max to 0, or rather to 1, and I'm also going to reset our minimum to 1. And the reason I'm going to do this is because I don't want to kill our product, right? I'm just going to say that zeros are ignored. We don't really care about zeros. And the reason I'm setting this to 1 is because then when we start introducing new values like 3, it's just going to be 1 times 3, right? Which is going to end up being 3. So 1 is like a neutral value for us. So those are the main things. We want to maintain the max and minimum of our product, and we want to handle the 0 case by resetting everything to a neutral value like 1. Okay, so now let's code it out. I'm going to say our result is initially just going to be set to the max value contained in nums, because we at least have to set it to some value. We can't just initialize it to 0, because what if we had an array with just one number and it happened to be -1, right? In that case, this is our max product, which is even less than 0. So 0 is not a good default case. And I'm going to maintain the current min and the current max, and I'm going to initialize these to 1 each, because we know 1 is like a neutral value. And then we're just going to start iterating through every single number in our input array. We know that if we ever get to a 0, we do not want to handle that. We don't want to add that as a part of our product. So we don't want to mess up our current min and max by multiplying it by 0, because then it's going to stay 0 forever. So instead, what we're going to do is we're going to reset our min and our max to 1 each, and we're just going to continue to the next iteration of the loop. If this doesn't execute, that's when we're going to actually do our code and recompute the current min and current max. So our current max, how are we actually going to compute it? Well, in Python, it's really convenient for us, because we can say, okay, the current max could potentially be the new.
I don't get this part here. Doesn't make any sense for me. Because shouldn't you keep storing the maximum? Well, let's see.
Number that we just found multiplied by the current max. If the current max happens to be positive and n is positive, it could also end up being the input value n multiplied by the current minimum, right? What if n is negative and current minimum is negative? Then this could end up being a positive number, which could be our current maximum. The third option is n itself, because what if we had an input such as -1 and 8? Well, in that case, the current min and max is going to end up being -1, and either of those numbers multiplied by 8, which could be our hypothetical n value, is going to end up being -8. So 8 it's by itself, which is n, is the maximum. And the fun thing about Python is that, look, we just put 3 values into our max function. Some languages don't allow for this, but there's obviously ways to get around it. And so now that we have our current max, we can do the exact same thing for our current min. So min. So we can actually take all 3 of these values, copy and paste them, and then put them in the min, because we want whatever the min containing n is, and it could be anything. It could be n times current max, n times current min, or n itself. So an example would be -1 and -8. If we multiply these together, we get a +8, but we don't want that. We want the minimum, which could be just -8 by itself, which would be this third case. But this is where I always end up with a bug. So you see how we actually recomputed the current max, but we want to use the old current max. So I'm actually going to have a temporary variable up here, temp. And before we end up reassigning current max, I'm just going to compute current max times n and then save it in temp, so then we can use it down here. So we're going to replace this with temp. So this way we're always keeping track of what the current max is and what the current minimum is. And so we can update our result after each iteration of the loop. And we want the max product, so we can take the maximum of result itself, because result could still be the max, current max, and current minimum. So that's actually it. Like, we've done it, and we can now just return our result. And so this is actually not that much code. And it's not even, like, when you look at it, it's hard to recognize that it's even a dynamic programming problem, because it's not like we're storing an entire array like dp and then having an array. We're just maintaining 2 values, current min and current max. And what they tell us is, for, let's say, for example, we were at this value n, then we're going to have the current maximum of this subarray and the current minimum product of this subarray. And then when our n gets shifted to the next value, we're going to have the current maximum of these 3 and the current minimum product of these 3. And then by the time our n value is out of bounds, we will have the current max and the current minimum of the entire array computed. So it runs efficiently, and that's because we're only iterating through the input. So instead of being n squared, the time complexity is just big O of n. The memory complexity is big O of 1, because we are not using an array. We're just using single variables. I hope this was helpful. If you enjoyed, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon.
Yeah, I'm not sure if I really get it completely, but let's move on. Word break. Given a string s and a dictionary of strings word dict, return true if s can be segmented into a space-separated sequence of one or more dictionary words. Note that the same word in the dictionary may be reused multiple times in the segmentation. This, damn. Oh, they passed the dictionary of strings word dict. Return true if s can be segmented into. What I'm thinking about is creating this stack and then appending to the stack. I wonder if I can do that, actually. So I'm pretty much gathering the words in the stack until I find the string in the dictionary. Maybe I don't need to use... it's probably better if I do like this. And maybe I don't need another function. That's the issue. Oh, but maybe if I do the other way, that's because I'm decreasing the size and I'm still looping through the same thing. So maybe I need to separate each function, because I think that this logic should work. So pretty much I loop inside of the first string until I find Yeah, so what if I separate this into a function? Or maybe if I do it recursively, then I pass the size, I pass the string. Yeah, like this, let's say. I have the string, let's call it st, and then the I. I'm just gonna copy this here. So if word is in the dictionary, word would be this string. Yeah, but then I have to, well, I can just make this thing here outside. Yeah, but then the issue is that I'm emptying the word each time. Or maybe not actually. Yeah, maybe not because of the if condition. New st. And then here I just call dfs with new st and I plus 1. Yeah, but I still think there's a problem there because of the index. So but maybe I don't need I, maybe I can just decrease the string one by one through the call. Yeah, but then I'm calling here. And maybe I don't need to change the string, the initial string. So let's say if I erase this stuff here. Yeah, I don't see why this wouldn't work. Maybe I'm missing something. So the string is cats and dog. Cats. And it's supposed to be false, but there are different words in the string. So again, it's the problem. I don't understand exactly what they're asking me to do. Now, clearly, it shouldn't be as easy as this one. So it's probably the same issue that I had in the previous one. I'm trying to understand string S and dictionary of string words. Return true if S can be segmented into a space separated sequence or dictionary words. Same word in the dictionary may be reused multiple times in the segmentation. The same word in the dictionary. I don't understand why this is false. Don't you have cats and here? I'm gonna have cats and. What am I missing here? My mind should have two words here. Cats and. Maybe it's because I stop at cat, but even if I stop at cat, there's still sand there. Yeah, the thing that I'm missing also is the combinations. Because if I stop at the first string, then I might miss another one that would need the letter from the previous one. So in this case, if I stop at a cat, then I miss cats. But it still says one or more, so of one or more dictionary words. So I'm not sure. Yeah, I don't like this problem in general. Not the problem, but the way that they phrase this. Or maybe, yeah, I don't know, something with me. I just don't understand. Because it should be true to me here. I'm just gonna look at the solution of this one.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem word break. So we're given an input string and a dictionary of strings called wordDict, and we want to return true if and only if S can be broken up into separate strings such that every separate string in S is also found inside of our wordDict. And we are allowed to use words from the wordDict multiple times. So for example, let's say we're given an input string LeetCode, and we're given a word dictionary of words called Leet and code. So obviously, in this case, we could split this string right into separate strings, Leet, right? Break it down in this middle position, and then the second string would be code, right? So clearly this can be broken up into words that are found in the word dictionary, so therefore we are going to return true. Now, what if we took code outside of our word dictionary? Well, then in that case, this portion Leet is a word, right? But we have no matching word in our dictionary for the remainder code. So in that case, we would have to return false. And let's say we had an input string instead called Leet and Leet again, right? So two Leets in a row would we return true? Yes, because we're allowed to use this word from our word dictionary multiple times, right? Clearly it matches this, and it also matches the first portion. Now let's start off with a brute force approach. How would we even structure a brute force solution? Well, there's actually two ways to do it, but one of them happens to be more efficient, and I'll tell you why. So one thing we could try for an input string like this one, we could check, okay, the first character, right? Basically the first prefix of the string, L by itself, right? Is this a word that's found in our word dictionary? It's not, right? So let's try maybe the first two characters together are a word, right? That's not it either. We would try the first three, right? Basically we would try every single portion from the beginning until we found a matching word that does exist in our word dictionary. And we know that we are going to find one like this, right? The first four characters of the string are a word, right? So once we found that, what are we going to do? Clearly we have a subproblem, right? We found a matching word for this portion, but now we want to know, can we break up the rest of the string with words from our dictionary? So that's kind of how we're going to do it, right? That's what's going to be the subproblem basically. So instead of starting from the first position in the string, we would start at this position in the string and try to word break it. Now in this approach, what we're going to basically be doing potentially is from every single starting position, right? We're going to check every prefix, right? So from the first starting position, we might also get, if this happened to be a word, then we would start at this position and then do the same thing for this, right? Every word starting here. So basically we're going to try every word, how many different words are we going to end up trying? We're going to try, let's say n is the size of our string n, and we're going to try basically from every single starting position to the end. So that's going to basically be n times n. Now, we could also do it a different way. Instead of trying every single possible, prefix, let's just check every word in our word dictionary and see if that matches. For example, this first word is 4 characters long, right? So what we're going to do is we're going to check the first 4 characters in our string. Does this match this word? Clearly it does, right? So what does that tell us? That tells us now, we have the same subproblem as before. We're going to start from this next position now, right? And check. And from here, we're basically going to be doing the same thing, right? So we're going to check is leet, basically, the first 4 characters, does that match leet? This does not match leet, right? So now let's check the next.
Oh, I just realized that I can also use the substring from Python and look through the dictionary and then check if each word is a substring of the other one.
Word in our word dictionary and check does that match the characters over here. It does, right? We found code. So this is basically another way to do this problem. Instead of checking every single possible prefix, right, of any length, what we're going to be doing is we're going to be checking every single word in our word dictionary as the prefix. So instead of being O of n times n, we're going to be doing O of n because potentially we are going to be going through every single starting position, but we're going to be multiplying by the number of words in our word dictionary, which is, let's call it m. And the reason why we're going to be doing this approach is because it's going to be a little bit more efficient. And the reason is they tell us below in the problem statement that the max size of word dictionary is going to be smaller than the max size of the string. So this is overall probably going to be more efficient. Now this isn't going to be the overall time complexity. We are actually going to multiply it by another n because when we're checking, for example, this string, when we're checking does that match the first 4 characters here, that's also a n time operation because it could potentially be the size of the input string s. So this is basically going to be the overall time complexity, n squared multiplied by m. So I'm just going to basically show you the same formula that I usually do. I'm going to give you a quick illustration of what the decision tree would look like. Then we're going to understand how we could cache that to eliminate repeated work. And then by understanding that, we're going to go to the optimal dynamic programming solution, the bottom up approach, and then we're going to code that up. Usually the DP solution is a lot less code than caching. So we're going to be looking at our input string LeetCode. So I think that's a little bit better than LeetCode, wouldn't you say? So what the decision tree is going to be is we're going to start at the first position, right? For example, I equals 0. We're going to be keeping track of whatever index we're at, right? Because we know that if we can find a word, that matches neat, for example, then the subproblem is going to be, finding words that can match the remainder of the string. For example, if we did that, our I, instead of starting at index 0, would basically be starting at index 4, right? So that's what the subproblem is going to be. So really, we're only going to have one variable that we're keeping track of in this backtracking solution. And so remember, we mentioned we're not going to be doing it like this. We're not going to check every single prefix. We're going to have decisions in our decision tree based on the number of words that are in the word dictionary. So we're going to have a decision for neat, we're going to have a decision for leet, and we're going to have a decision for code. Now, what we're going to notice is when we try leet on here, right? Basically, leet is 4 characters. Therefore, we're going to check the first 4 characters of here, compare it. Does that match leet? It does not, right? We're just 1 character off, that first one. So basically, that means we're not going to continue down this path. Now let's try code. Does code match the first 4 characters? Definitely not. So we're not even going to continue down this path either. Of course, neat does match this. So we are going to continue down here. We're going to do 3 more decisions, basically 1 for every single word in our word dictionary. Now, one thing though is when we are starting here, we know we match the first 4 characters. So by this point, we are now going to be at I equals 4, meaning we're going to be looking at this part of the string. So as we can see, checking neat, that's 4 characters long. So let's check 4 characters starting from here. That's not matching, of course. So then we're not going to continue here. Leet, does that match over here? Nope. We're not going to continue down this path. Code, does code match this portion? Yes, it exactly matches. So therefore, we're going to update our I pointer again. Since we matched 4 more characters, we're just going to take I and add 4 to it now. So now I is going to be at 8, and 8 happens to be that exact position right after the end of the string, right? This is where index 8 is. Therefore, we basically know that we were able to match the entire string. Therefore, we know we can return true, right? Once we find a single true, that means we just terminate, we end the function, we can just return true, and the function is done. Now, from this example, it might not be super intuitive why we would use a cache, but let's say we had another path in our decision tree that led us to, for example, index I equals 5, right? And let's say we used all 3 decisions in that path, and let's say none of them yielded the correct result, meaning we were not able to word break this string from starting at index 5. So then we would return false from this path, right? And we would want to cache that. We would want to say that, let's say dp of index 5, right? We would want to set that to false. Basically, what we're saying is if we ever reach this same function call, if we ever tried it again, maybe, this decision tree could be really big. Maybe there would be another path from, somewhere over here where we tried index I equals 5 again. In that case, we would want to return false immediately because we saw from here there was no possible way to break it down. Therefore, we don't need to redo all of that work if we, try the same exact thing. So we discovered that our base case is going to be dp of 8 because 8 is the length of the string, basically is going to be true, right? If we can ever get to that last index, we're going to return true. So what we're going to do is now do the bottom up approach, right? We're going to go through every single index in reverse order, right? So we would start at the last character, which is position 7, right? And see, can we word break the remainder of this string? And we would try every single word, right? Like neat, does neat match this string? Well, they're not even the same size, right? If we tried to match neat on 4 characters starting from here, we would go out of bounds of this string, right? There's not enough characters. So of course, this is going to be false, right? It wouldn't match neat. It wouldn't match the other 2 words in our dictionary either. And that's obviously going to be true for dp of 6, dp of 5 as well. So both of these are also going to be false, right? Basically, if we started from 6 or if we started from 5, we would not be able to match any of the words in our dictionary. But now if we start here, index 4, so we're now trying to figure out dp of 4, is that true? Well, yes, it is, right? It doesn't match neat, it doesn't match leet, but it does match code. So we are going to set dp of 4 equal to true. So now let's keep doing it until we get to the first character. So now we're going to be trying from dp of 3, right? So starting from this character, are we going to be able to match any of these? Well, none of these words even start with a T, so of course we're not going to be able to match. So dp of 3 is going to be false. What's dp of 2 going to be? It's also going to be false because if we were to start at this character, this E, would we be able to match any of the words in our word dictionary? Of course we would not. And what about this position? If we started here, would we be able to match any of the words in our word dictionary? Again, not. So dp of 3, dp of 2, and dp.
Again, it's the same pattern that I'm missing, is that I was thinking about testing from the beginning, but what if in the beginning it doesn't match anything, and then the other words are the beginning of the letters? And then the next thought I would have is probably the sliding window again, of trying to make the window, but clearly it's different, a different way.
P of 1 are going to be false, meaning we cannot word break this string if we start at any of these three positions, basically. Now we're finally at the result that we were looking for, dp of 0. Is dp of 0 going to be true? Well, let's take a look. So we're starting at the first character in the string. Can we match any of the strings? We can't match Leet, we can't match code, but neat, it does match this portion of the string starting at index 0. So then the question becomes, we're asking, can we break the entire string starting at index 0? So now since we did match the first 4 characters, we want to know, were we able to match the remainder of the string, right? So we want to know, starting from here, were we able to match this string to words in our word dictionary? Now this is why we computed this bottom up, right? Because this is index 4, right? Notice how we already computed index 4 over here, right? It's the one that's highlighted in green because it was true. We were able to do it. So basically the equation that we would use for this is going to be dp of 0 plus the length of the word that we were able to match with, and we know the length of the word neat is going to be 4. So basically we can replace this length of the word with 4. So 0 plus 4 is just dp of 4. We know that was true, so we can set dp of 0 equal to true. So this is basically the result, right? This is how we're going to compute it, and this is what we're going to assign dp of 0 to. And once we've done that, we've computed the result. We know we can return true for the overall function. So with that being said, let's jump into the code. So our cache is going to be, let's say, a one-dimensional array, right? Because for every position I in the string s, we are going to have a value. So we're going to initialize this to false. It's going to be the length of the string s plus 1 for our base case, and we are going to initialize our base case. We know that it's the last position, basically the position out of bounds of the string, so the length of s, and we know that's going to be set to true. That's our base case. So now we're going to go through every position I in the length of the string, starting at the last index and working our way to the beginning. So that's why I'm using the decrementer of -1, and we're going to go up until the beginning of the string. And for each position I, we want to try every single word in our word dictionary and see if the word matches this portion. So first we have to see if starting at position I, the string s even has enough characters for w to be compared to it. So what we're going to do is we're going to check I plus the length of w, and we want to know, is it less than or equal to the length of s? If that's the case, then that means there are enough characters in s for us to compare them. So that's exactly what we're going to do. If this is true, then let's compare. So we want to know if that's true, and if s starting at index I going up until I plus the length of w. So basically, let's say w was 3 characters, then we want to know the first 3 characters in s starting at index I, are they exactly equal? If they are equal, then we want to know, okay, so dp of I is going to be set to dp of I plus the length of w, right? That was the relationship. We got I plus the length of whatever the word happens to be. Now, if we got a single way to word break this starting at index I, that means we can basically stop this loop, right? We don't have to look at every single word in the dictionary. If we found at least one way we were able to word break it, then we're going to stop. So basically, if dp of I is true, then we can break out of this for loop and then move on to the next index. So we're going to start basically at the last index, keep going until we've gotten to index 0, and then once we've done that, we know we can actually return that, and that's going to be stored in dp of 0. So believe it or not, that is the entire code, about 10 lines, I think, and this is a pretty efficient solution, as you can see. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel.
Pretty much the same way that he solved the previous one. I had the feeling it would be very similar, but I still don't understand this really well. False length equals true. So it makes the last index of the array equals true, the rest equals false. Then a nested for loop with the condition. Yeah, I don't know.
A lot, and I'll hopefully see you pretty soon. Thanks for watching.
Don't spend too much time. Longest increasing subsequence. Given an integer array nums, return the length of the longest strictly increasing subsequence. Subsequence is a sequence that can be derived from an array by deleting some or no elements without changing the order of the remaining elements. Subsequence of the array is a sequence that can be derived from strictly increasing subsequence. Subsequence is a sequence that can be derived from by deleting some or no elements without changing the order of the remaining elements. Also, you can remove elements in between, and they all have to be increasing in the final one. Yeah, that's another hard one. Because the have to count is the same thing from the previous ones. You have to keep track somehow and then remove depending on the whether or not it's increasing or decreasing. Hmm. Yeah. I think I'm gonna look at the solution for this one. I think I already looked enough dynamic programming problems to understand what I'm trying to get through with this round of, because the main point of doing this fast is so I can understand the patterns behind them and the structure of each problem. It's not necessarily to be able to finish them, and I think I looked enough, because now it's counterproductive, I think. Because in order to be able to solve this one I had to spend more time trying to understand the solutions of the previous ones. So I know how to come up with the solution myself. But then that's not the point of doing this phase. So I think I'm gonna just look at the solution for this one, and depending
Hey
on how
everyone,
similar the
welcome
other
back.
problems are in dynamic programming, the 2D, I might go really fast through them as well, and then I take more time on the other ones. And I think I got a understanding now of how all of these problems are gonna work. Is either gonna be top down or bottom up. If it's bottom up, it's gonna create the two nested for loops to get all the possibilities. Then gonna create an array at the beginning to analyze these possibilities as he moves through the other ones. And then what's gonna be the difference in the problems is gonna be the way you move in the nested for loop based on the conditions you want to achieve. And on the top down, it's gonna be the same thing, but the conditions that are gonna change are gonna be inside of the recursive depth first search function. So I think I'm gonna look at the
Solve another
solution.
problem today, longest increasing subsequence. And this is another tricky dynamic programming problem. And I'm gonna show you how to go from the recursive solution to the dynamic programming solution. So we're given an array of numbers and we just wanna return the length of the longest increasing subsequence. And if you don't know what a subsequence is, it's basically like, let's say this is our input array. We're basically taking a subarray, but that subarray does not have to be contiguous. So like we have from here, so subsequence is 3, 6, 2, 7. Basically we took this subarray and we removed 1, 2 from it and we removed a 1 from it. And now it's 3, 6, 2, 7. But you notice about this subsequence, it's not in increasing order, right? We have 6 and then we have 2, that's not increasing order. So this is not a increasing subsequence. So in this example, we're given about 9 elements and we want the longest increasing subsequence, which we see is this. And so how do we get that subsequence? Well, you go from 2 all the way to 101, but you notice that unfortunately, this is not in increasing order. We have a 5 and then we get a 3 right after. So we actually have two choices. If we remove the 3, we have an increasing subsequence. If we remove the 5, we also have an increasing subsequence. But we just care about the length, which in this case is 4, so we return 4. So the first idea you might have is brute force using depth first search. So let's say that this is our input array. So we have 6 elements. If we want to know the brute force, meaning we want to generate every possible subsequence, we have a choice for each value, right? So for the first 0, we have a choice. Are we going to include this 0 in our subsequence or are we not going to include it in our subsequence? So in reality, for each value, we have 2 choices. Now, when we get to the next value, we also have a choice. Are we including it or not? So again, we have 2 choices if we want to generate every possible subsequence. So we do that for every single value. And then we see that there are actually 2 to the power of n possible subsequences where n is the number of values given in our input array. So already you can see the time complexity is not going to be great, but can we take this brute force approach and then somehow modify it to get a better solution like n squared? So let's look at another example, and this time we're going to do depth first search with caching, and we're going to see how that improves our time complexity. So we have an example of 4 elements, so it's kind of obvious that this is our longest increasing subsequence, so the result is going to be 3 elements. But how can we do this with an algorithm that's efficient? Well, let's start out with the brute force approach. Let's check all subsequences starting at index 0, and then repeat that starting at index 1, starting at index 2, and starting at index 3, right? So these are the indices. So we take one decision to start at index 0, we take one decision to start at index 1, one decision to start at index 2, and one decision to start at index 3. So in these cases, these are going to be the subsequences we have so far. So we know index 0 has value 1, index 1 has value 2, index 2 has value 4, index 3 has value 3. So now let's go along the first path, so index 0. So we know if we start at index 0, we have 3 values that come after it. So we can try all 3 of these possible decisions. So we can go along index 1, index 2, and index 3. And we see that all 3 are possibly valid because all 3 of these values are greater than 1. So we can continue these subsequences. So we know index 1 has value 2, index 2 has value 4, so we can add a 4. Index 3 has value 3, so we can add a 3 to our subsequence that originally was just 1. So now we took index 0 and index 1. So for here, we only have 2 indices that come after these 2 values. So let's continue our decisions. We see that both 4 and 3 are greater than the last value in our subsequence, which is 2. So we can choose both of these decisions. So if we take index 2, then we can add a 4 to our subsequence. If we take index 3, we can add a 3 to our subsequence. So now let's continue here. We have 3 values so far in our subsequence, and there's one index that comes after 2, index 3. It has a value 3. So can we add a 3 to our subsequence? We'll get 1, 2, 4, and then 3. But this 3 is not greater than the last value in our subsequence. So we technically cannot make this decision. So we cannot continue to increase this subsequence anymore. So we can mark this as reaching its limit. We cannot continue it anymore. What about this one? Well, it stopped at index 3, which was over here. So are there any elements that come after it now? No, there's not any elements. So this subsequence has also reached its limit. So we cannot increase it anymore. But so now let's focus on this caching part. What kind of repeated work have we eliminated? Well, let's just do this out of order. Instead of doing these first, let me show you what happens if we try to extend the 3 now. We try to get another element, right? We started at index 3, but we know that no values come after index 3. So this one cannot be continued. But what do we know about index 3? If we start at index 3 and we want the longest increasing subsequence, we just get a single 3. So that tells us that LIS starting at index 3 is 1. We don't need to repeat this work. And isn't that what we just learned over here? Even though this subsequence is length 3, we are talking about starting at the 3, and we noticed we could add a 3 to it, right? This was the element that we added, but as soon as we added that 3, we could not increase this subsequence anymore, right? That's what this X tells us. We were only able to add 1 element if we start at index 3. And that's exactly what this 2 told us as well. If we start at index 2, we can add a 4, but this 3 that comes after it cannot be added. We cannot include that, and there aren't any more elements to add. So as soon as we finished this and we found this X, meaning we could not go any lower, we knew that the longest increasing subsequence starting at index 2 is also 1. So therefore, if we start at index 2, we cannot go any lower. We cannot continue this. And we don't even have to attempt to do that. And what about this branch? So if we started at index 1, we would start with the subsequence of 2, right? That's what this tells us. And so now I'm going to do some more stuff, right? I'm going to choose the next indices 2 and 3. But wait a minute, do I actually have to do that? Because look over here. We started with index 1 and we already did that. So when we started with index 1, we saw we had 2 choices, a 2 or a 3 index, right? We could choose this or we could choose that. We saw both of them ended, right? We could not continue either of them. So if you want the longest increasing subsequence that starts at index 1 over here, no matter what you choose, the subsequence is going to be length 2 either way, right? Because if we start with a 2, then we can add a 4 or we can add a 3, but we cannot add both of them. So we can mark the longest increasing subsequence starting at index 1 to be length 2. So we actually don't even have to go down this path once we already go down here because it's just going to be repeated work. And we also see for these 2 trees that we have not finished yet, once we add a 4, the longest increasing subsequence at index 2, which is where 4 is at, is going to be 1, so we cannot continue this anymore. Similarly, once we add a 3, we know no values come after it. The longest increasing subsequence starting at index 3 is just 1. We cannot increase this anymore. So when we finally, in our depth first search, get back to the root, we're going to see that the longest path is one of these, right? Either that, or of course you could go down this direction, but either way, the longest increasing subsequence starting at index 0 is going to be 3. And so when you look at these 4, right, because these are our subsequences, these are the longest subsequences starting at each index, the greatest one is 3, and so therefore the result is 3. But now if you actually want to do the dynamic programming solution, you might notice how we're doing this recursively. We're kind of starting at the last index, right, 3, and then working our way up backwards to 0, so then going back here. So can we use that to do dynamic programming? So now let me show you the dynamic programming solution, and it's actually easier than you might think. So we're going to start at the last index 3 and then work our way backward. So we know this is kind of the base case, right? No values come after it, so the longest increasing subsequence we can make from here is just going to be length 1 anyway. So we can say the LIS starting at index 3 is just 1. That's the max length. Now, how do we get the longest increasing subsequence starting at index 2, which is just 1 shifted to the left? Well, one possibility is just 4 by itself, right? So that's one possibility. It could just be 1, or it could be 1 plus the longest increasing subsequence starting at position 3. And what this means is if we take both of these, right, because LIS of 3 is just 1, right, so 3 by itself, but we're only allowed to do this if the value nums at index 2, which we know is 4, is less than nums at index 3, which we know is 3. Is this true? This is not true. So we are not allowed to do this. So normally we would take the max of these 2 values, but we know that the condition to take the max of this does not satisfy, so we only have one choice, 1. So the LIS of this is going to be 1. I'll put it over here like in the corner. So again, we're going to work our way backwards. So let's get the longest increasing subsequence, one index back at index 1. So we're going to do the similar thing that we just did. So we know we could take a subsequence 2 by itself, right? That's one choice. 1 is a choice, length 1. We also have a choice, 1 plus the longest increasing subsequence starting at 4. And we're allowed to do this because 2 is less than 4. So it is increasing. The subsequence is increasing. So another choice is 1 plus LIS of 2. And another choice is LIS starting at index 3 because 2 is less than 3, right? 2 is less than 3. So the subsequence is in increasing order. So 1 plus LIS of 3. Now we know that this is 2 and this is 2. So it doesn't really matter which one we do. The LIS of 1 is going to be equal to 2 regardless. So now we want the longest increasing subsequence starting at index 0. And we're just going to repeat what we just did. So we can take 1 by itself, which is just 1. Or we could take 1, add it with the longest increasing subsequence starting at 2. Or this longest increasing subsequence starting at this index or this index. So we know we're going to get 1 plus 1 from here. We're going to get 1 plus 1 from here. And we're going to get 1 plus 2 from here. And we're allowed to do all of these because you notice 2 is greater than 1, 4 is greater than 1, and 3 is greater than 1. So they're an increase. So they are in increasing order. So then we know that the longest increasing subsequence of this is going to be equal to 3, which is what we want. So this is a much better solution. The dynamic programming solution is much better than brute force because the time complexity is O of n squared. But why is it O of n squared? Well, you see we're working backwards. We start at 3 and then we check every position afterwards, which is not too bad, right? So then we iterate through basically every value here. When we start at 4, we have to look at every value that comes after it. There's only one value that's good for us. So we iterate through these 2 values. When we start at 2, we have to check these subsequences starting at these 2 values. So then we have to end up iterating through 2 and every value that comes after, and we do the same thing for 1. So we iterate through 1 and every value that comes after. So you can tell by looking at this pattern is similar to an n squared pattern. So now let's finally write the code. So we know we're going to do this dynamic programming style. So let's have a cache or a list. It's initially going to be set to 1. Every value is going to be set to 1. It's going to be the length of the input array that we're given. So every longest increasing subsequence starting at every value or every index is initially just set to 1. We're going to try to find what the max is. So we want to iterate through every index in the range of our input array, and we want to do it in reverse order. So that's what I'm going to do in Python. If you're not familiar with Python, this might look a little weird, but basically what I'm doing is starting at the last index and then going all the way to 0. And just like I showed in the example, we're going to start at index I, like this could be I, and then we want to iterate through every subsequence that came after it. So I'm going to have another nested loop for j in range. So starting at I plus 1 and then going to the end of the input array. And before we can update LIS, we want to know, is the value at I actually less than the value at j, because j comes after it. If we want this to be an increasing subsequence, this condition has to be true. And only then are we allowed to update the longest increasing subsequence at index I. And we can set it to the max of itself or the max of 1 plus the LIS starting at j, because we know for sure j is going to be in increasing order with I. And literally that is it. We made sure to evaluate that it's in increasing order. We did it backwards. We made sure to cache the repeated work. What do we have left to do? Well, we want to return what the max is. How can we do that? Well, in Python, you can just take a max of a list. So whatever whatever the greatest value is in here is going to be returned. And there actually, so this is O of n squared, and there actually is a better solution, big O of n log n, but I really doubt your interviewer is going to expect you to get this on your own without a hint. If they do, I would personally just walk out of the room. But I hope this was helpful. If you enjoyed, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. N log n, but I really doubt your interviewer is going to expect you to backwards. We made sure to cache the repeated work. What do we have left to do? Well, we want to return what the max is. How can we do that? Well, in Python, you can just take a max of a list. So whatever whatever the greatest value is in here is going to be returned. And there actually, so this is O of n squared, and there actually is a better solution, big O of n log n, but I really doubt your interviewer is.
God damn. Now I want to know the better solution. I wonder if there's anyone. Probably there is. I can search it up. After I finish the list and I'm going through the problems again, I'm going to look at the solutions after solving the problems. I'm going to look at the solutions. So there's probably someone that did with the better solution. Unique path. There's a robot on an m times n grid. The robot is initially located at the top left corner. The robot tries to move it to the bottom right corner. The robot can only move either down or right at any point in time. Given the two integers m and n, return the number of possible unique paths that the robot can take to reach the bottom right corner. The test cases are generated so that the answer will be less than or equal to this. God damn, this one is going to be very hard. Explanation: from the top left corner, there are a total of 3 ways to reach the bottom. Right, down, right. Down, right, down. So it goes all cells in one direction. Oh no, it's a different example. I think I got it. So let's think about this example with this bar, but so this has more than 3 ways. So I think this is gonna be similar to the graph one, where you have that first search and then you have a set with the path. Yeah, I remember these rows and columns making it equal to. Oh, they don't give you the board this time. Just the sizes of the grid. So it's a different approach probably. Oh, it has to be if it's on a different section. Obviously, I can create the grid, create the board from the dimensions. So create the matrix and then get the rows and columns and then try to do the depth first search, but I don't think that's the point. I also don't remember really well the solution for the other ones, the graphs. I remember that there was that first search and then, oh yeah, you move each time at one direction. So you call recursively 4 times depending on the direction of the square. To get all possible situations, then you append to a set or something like that to keep track of the path, depending on the problem, but I don't remember really well. So what's the difference between on those ones and this one? So maybe you can do a nested for loop here and then solve the same way as the other ones, or have then 1 times or 1 times length of m. And then you begin with for I in range length minus 1 minus 1 minus 1. And the thing is that there are 2 dimensions, so here would be n probably. Or maybe it is like the graph ones, because each square is gonna have 4 different directions that it can go. So maybe I should try to do the DFS stuff. Rows, columns. So I think this is what I remember from the previous ones. If y bigger than 0 or smaller than 0 should be. And then I'm getting all possible directions, but now I need to create a set, so each path. And I remember this was different because rows and columns was the length. In the other problems, because I already had the board, and now I'm making them equal to the lists, so that might be different. Because n is the height. So maybe columns should be n, and then rows should be m in this case. Or no, rows should be n and columns should be m. So maybe this is unnecessary at the beginning. Just put m here. And then I should probably, yeah, then I store each direction on the path. And the issue is that I think I still need to make the matrix with all the possible combinations. Because I need a way to keep track of each square in the path. But how I'm gonna make it so I have the unique path? Seems to be another thing that I'm also struggling at. That I remember from the graphs as well. About understanding how the path is gonna be stored in the set or memorized. Because it doesn't make sense to me to store more than one at a time. One value at a time. I think that's the biggest issue that I'm having is understanding this tree stuff. About how to store, how to think about the way you should store each path. It's really confusing to me, and I didn't clarify on the previous problems. And since should be a common thread, not only on dynamic programming, but in the other kinds of problems. So each square has 4 possible outcomes. And then these 4 possible outcomes increase in the size of the tree, because from each one of them there's another one. But to create that tree structure, I can't think about the way to do it. I think I know what I should do it. I just still can't come up with the way. It's pretty much the same logic from the previous ones. For each one, you create a tree, a decision tree, and then from that decision tree, you're gonna have the paths, and then you memorize some parts of the decision tree to make it more efficient. But I still struggle with trying to think about how to memorize that and how to create the decision tree each time. And I guess the issue is that I'm thinking about creating something else here and then appending all the possible solutions until it gets to the end. But if I do that, then I can check again. If when I'm exploring a new path, I can check to see if the path already exists on the previous one. And it's something that it's the same mistake I made on the other ones of thinking about it this way. But for some reason, I can't really understand the other way to go about it. I still haven't captured the fundamental distinction there between the way that I'm thinking. Because it's not just the way that I'm thinking, it's the way that I'm approaching the problem and the way that he approaches the problem. I should find the optimal solution. And I guess it's probably because the way that he's explaining the solutions, it's almost like he's coming from, because he is right, coming from the position that he already knows the solution and he's explaining. It's not so much coming from the position of walking through the discovering process of finding the solution. I think that's the difference. Because when he explains from the position of already knowing the answer, it doesn't give you the insight of how to go about figuring out. That makes sense. It's not that it is bad, the explanation, but it is good. It's just that I think I need to find. The reason I think about this is uh, after I'm done with this and I go in depth into each problem, I need to find a gap between his solution, the way that I'm thinking, and something that can help me bridge the gap between the two. And I don't think his videos are gonna be enough to understand how to think in that way. Because I think he's approaching the how, but I wanna understand the why. That's the difference, I think. Because each time he's explaining these problems, he's going through the steps he takes to solve the problem, but not why he decided to take these steps. Or maybe he goes into that, but it's kind of hard to uh, kind of understand how to go about it. But maybe it could be as well that I'm not spending a lot of time really understanding each solution from the previous one. That could be also the thing. Because if I spend a lot of time on the previous ones, then I would probably be able to capture the fundamental thing that I'm missing on each one. So what would be the best way possible to phrase the question of the gap there? So I'm thinking about how to create tree and then memorize. I still don't know. Let me think. Yeah, because what I want to try to do is capture the fundamental thing about the construction of the tree that he creates each time, either bottom up or top down. And I need to phrase the question. The hardest part is coming up with the question. Once I have the question, then I think it's gonna be a lot easier to learn on the next round. It's not so much how to solve or how to create the tree. I think it's how to figure out which branches, I think. How to spot which branches are going to be necessary. How to spot which branches are going to be necessary, and how to know whether or not to start at the end or the beginning, bottom up or top down. I think those are the parts that I'm struggling with coming up. Is understanding which way to go about it, which way to make that makes more sense to go about it when building the tree. And I'm not really sure if I understand, if I can visualize really well how the tree is being formed as well in a lot of these problems. Another thing that I'm struggling with, I
Hey
think.
everyone, welcome back, and let's write some more LeetCode today. So today let's look at unique paths. So this is a dynamic programming problem, and it's a relatively straightforward one compared to a lot of more difficult dynamic programming problems. We are given a m by n grid, and so the top left in the grid is always going to be our start value. And so from our start value, it's like a game. We have two choices no matter what position we're at. We can only move right or we can move down. Those are our only choices. We can't go diagonal, we can't go up, and we definitely can't go left. So our goal is to reach the end position or the finished position. That's always going to be the bottom right. So we start at the top left, but we want to go to the bottom right. And the only question is, how many unique paths are there to get to the end position? So at first, this kind of seems like a recursive problem, right? So we have two choices, right? We can go down or we can go right, and then that's a sub-problem. One thing to notice is, see how from the start position, we are actually able to move to any position in the entire grid. But if we move right from this position, what are the possible spots we can go to? Well, we can go right and we can go down, so we can actually go to any spot here. But notice we will never be able to reach these two elements if we start from here. And some Similarly, if we go down from here, then what positions can we reach? We can reach any position to the right or below, but we'll never be able to reach any of these positions. And another thing I'll notice is literally any spot in the entire grid, the nature of this grid, and since we can go down and we can go right, any spot in this grid will be able to reach our destination. So we don't have to worry about not being able to reach the destination. So yeah, you might try this problem recursively, right? So we have two decisions, go down or go right. And that's great, right? So now from here, we also have two choices, go down or go right. From here, we have two choices, go down or go right. You kind of notice though, there's some repeated work. Obviously, we can get to this position two different ways. So in that case, we're gonna end up doing repeated work, right? From this way that we got here, we can go down and we can go right. And we're gonna repeat that over here, right? Go down or go right. So if we're doing depth first search recursively, one thing we can do is have a cache. So for every row, column, position. So for example, in this position, we cache the result. So if we ever reach this spot multiple times, we will be able to store that and we won't have to run depth first search again because depth first search is pretty expensive. And so what is this value even going to store? Well, this is recursive. So for each position, we're actually calculating the number of ways we can reach the destination, right? And if we can compute that for every single...
That's the thing. I'm having difficulty visualizing because I already understood this. I think I got it, the main fundamentals. But I'm having difficulty visualizing how the tree is going to be. How can I store the state of the tree at each step? That's the biggest problem. And how to use the cache here to store that state. So when I'm trying to construct the thing, because I can't visualize how it's gonna be, I don't know exactly how to set up the logic inside of the depth first search to create the thing. That's the biggest problem I'm having, I think.
Like square, then we can compute that for the original square, right? Basically what I'm saying is the result that we're looking for is actually equal. So let's say we call this spot R, we call this spot down, right? So this is R for right, this is D for down. The result that we're looking for is actually the sum of R plus D, right? But then you might ask, well, how do we compute R and how do we compute D? Well, R is just gonna be, R has a value to the right of it and it has a value below it, right? So if we wanna compute this value, we can just take the right and down values and get them, right? But so what ends up being the base case? So with all that in mind, what ends up actually being the base case? Well, so this is the ending position, right? So how many ways from the ending position are there? How many unique paths are there to get to itself? Well, we can choose to define that as 1. So if we've defined that value as 1, we'll notice that things actually work out pretty nicely because let's take a look at this cell, right? We want to take the bottom value and the right value and then add them up and then that's what we're gonna put in this spot. But we see that there's nothing below it, right? That's out of bounds. What we can say is, well, we'll just define that to be 0, right? We'll define every value out of bounds to be 0. So if we ever need them, well, we can just say that they're 0. So then what becomes the value that we place in the cell? Well, we can take the right value, which is 1, and the bottom value, which is 0, add them together, and then we get 1. So we can just put a 1 over here, right? And you might notice, well, what if we want to compute the value in this position? Well, the exact same thing will take place, right? The value below is 0, the value to the right is 1. So we can say that there's one way from this position to reach the end result. And now what actually is that path? Well, we can't move down, right? That's out of bounds. So we can only choose to move right, and then we'll be able to get to the result. And you can see that's true for every position in the bottom row. So we're just going to fill these to be 1. And you might be able to see how we are going to arrive at the dynamic programming solution now. So the first thing for us to do is to compute this bottom row. Now let's start doing the next row, right? Because our ultimate goal is to be able to do this value. We can work our way from the bottom to the left, and then from here to the left, and then keep doing that, and eventually we'll arrive at the result. So what about this position? Well, it has a 0 to the right of it because the right is out of bounds. It has a 1 below it. So we'll take 0 plus 1. Again, we get 1. Now what about this spot? This spot actually has a value below it and a value to the right of it. And those values are 1 and 1 respectively. So the sum is going to be 2. And that makes sense, right? Because if you start here, there's one path going to the right and then going down, right? That's one path to get to the result. And there's another path going down and going right that lets us get to the result. So it makes sense that this would be 2 unique paths to get to the result. And from here on out, it's basic addition, right? So down is 1, right is 2. Add those together, we get 3. Here we get 1 plus 3, that's going to be 4. Add this together with this, that's going to be 5. Add these two together, that's going to be 6. Add these two together, that's going to be 7. And so you notice now we have filled in the second row. It looks a little bit different than the first row, right? The bottom was all 1s. And now the only thing for us to do is to get this last row. So we look down and we look right, that's 1 plus 0. So we're going to get a 1. Notice how the entire first column is 1. That's actually always going to be true, right? Because think about it, from any position in the rightmost column, the only decision we can do is move down. So there's only going to be one path to the result. So this is going to be 2 plus 1. This is going to be 3 plus 3. This is going to be 4 plus 6. This is going to be 5 plus 10. This is going to be 6 plus 15. And so finally, we are at our start position. So we can take the bottom and right values, 7 plus 21, add them together, we get 28. So that tells us if we start here, there are 28 different paths we can use to get to the result. 28 unique paths. And when you look at the picture, it actually looks more like a math problem than a coding problem, right? And that's because it is. You can actually calculate the number of ways from the top left, I think in constant time if you have like a math equation, but I don't know a ton about it. I'm just going to stick to the dynamic programming solution. So let's do what we just did in the picture. So I'm going to have a row, and this is initially going to be the bottom row. It's going to be the length of the number of rows that we have, which is n. But since it's a grid, you could probably use either m or n. And so since we know the bottom row is going to be all 1s, we can start going through the other rows. So we can go through all of the other rows except for the last one, so m minus 1. And for each row, we're going to compute a new row. So this new row is going to be above the old row. And so it's going to be the same dimensions, of course. We'll initialize it to all 1s. And to avoid the edge case of having to check out of bounds, what I'm going to do is go through every position, every column except the rightmost column. And we can do that like this because we know the rightmost column, or or the last value in every single row is always going to be 1, right? I showed that in the drawing. And so we're going to start at the second to last position, keep going until we get to the beginning, and go in reverse order. So we're going from right to left. And we know that the new row, so if we're computing new row of j, it's going to be new row of j plus 1. So this is the right value, and the value below is just going to be the old row at index j. And so with this loop, we'll be able to compute the new row. And so after we do that, we can update the row. So the old row is now going to be set to the new row. And so it's going to keep doing that until we end up getting the last, or rather the first row, the top row that we actually want to compute. So after this has been executed, that's what's going to happen. And what we actually want to return, though, is in that first row, which will be in this variable, we want the first value. So at index 0, that's what we're going to return. So now we can run our code. And by the way, so it is pretty efficient because we did this in O of n times n time, and the memory complexity is just big O of n.
And this part right here that I'm having trouble with visualizing, I think that's the biggest issue I'm having. But also he did differently than I was thinking about. +1 plus row j. Huh. Yeah.
And because that's the length of a row. So I hope this was helpful. If you enjoyed, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon.
So the thing is, I have to spend time, because I don't think I wanna search. I don't wanna learn related to the problems. I wanna capture the essence of the problems and figure out like the algorithm to solve the algorithms, if that makes sense. So I'm trying to think about, because I know what it's gonna do for solving these specific problems each time. It creates the list there, then that's a for loop, and then I apply some logic to get the paths in the first index of the list that he creates. But I'm trying to extract the fundamental parts of that and seeing how can I formulate a question that will allow me to study this in depth. The fundamental causes, not the facts. So trying to figure out how can I search for things that will allow me to understand this relationship between these nested for loops and the creation of these tree structures that allow you to solve these problems. And I'm thinking about that because if I can study through this question, then I can learn a lot more in a shorter period of time. Because instead of focusing on any specific problem, I'm gonna know the fundamental parts of all of these problems, and then I can think off the top of my head how to solve any of them. And I think that's more efficient than trying to solve any particular problem. But it's really hard to come up with a question that is good enough, or a set of questions to extract only the essence of the thing. I think I'll probably have to think more about it off stream or when I'm not recording. Because the main thing is the thing that the variables are the constrictions, I think. So each problem has its own restrictions, based on whatever the problem asks. And what doesn't change is this dynamics between these lists, the nested for loops, and the construction of the trees. So every problem breaks down the problem into a subset of problems, and then that's the indication that you're gonna use some recursion or this depth first search with the for loops. And it's just the connection there. How can I study that connection? if you could generalize these problems as much as possible, what would that look like? I think that's a good question. But the problem with this question is that it's going to be hard to find something on YouTube or Google that will give me good responses. So I need to search based on topic. That's the thing. And in the issue with searching for dynamic programming or graphs or anything like that is that most of the videos are going to be like the videos of this guy, which is just talking about specific problems. And it's going to be really hard to find videos that explain the fundamentals from which the problems are solved. So stack frames, recursion, things like that. I think that's what I'm trying to get through formulate questions for. Is in the essence of computing that goes beyond each specific problem. How does why is the case that these data structures work better for these types of problems, and what's usually the characteristics and the principles that go together in order to make the most optimal solution. So I think caching is one of them. Maybe that's something you can search for. Yeah, maybe that's a good point to start. Is how caching works, both in the memory, both in the problem in these problems, and but not just in problems, just in general. How and when to use caching. I think the how I already understand. Whenever you want to save time, because you're gonna have repeated decision trees. So maybe a good question would be also how you decide the breaking points that you're gonna cache. That's another thing. But it's not necessarily that, because I think deciding the breaking points is kind of easy, but formulating the algorithm that finds the breaking points is the hard thing, I think. So how to use the cache, maybe? How to use the cache to save computing and building a recursive tree structure. Yeah, I think I'm gonna study more about in this way next time I'm going through the list. I'm not gonna be so much concerned about solving the problems, but trying to understand in computing in general, not only for LeetCode, but for solving any kind of problem, creating libraries and that kind of stuff. That's why I'm approaching this more in this way. And I'm gonna watch YouTube videos and try to read stuff about these principles as well. Because it's a different way of thinking. That's the point, I think, of doing these exercises. Teach yourself a different way of approaching these problems. Longest common subsequence, given two strings, text 1 and text 2, return the length of their longest common subsequence. There's no common. Turn 0, subsequence of a string is a new string generated from the original string with some characters can be deleted or changing the relative order of the remaining characters. Of two strings is a subsequence that is common to both strings. Again, another question maybe that I can ask is how to decide. But this question is going to be hard to find things online, I think. Oh, bottom one. Top down. Like what is the key indication or the key indications that a bottom-up approach is gonna be best? That's another thing I'm struggling with. This example again, I think is gonna be similar to the other one, where it's gonna create this here and then make it equal to the length of one of them, and for loop. From the ends. Texture. +1. Probably. Something like that. Yeah, I don't know. I think I'm gonna look at the solution. And these ones I'm gonna spend more time, I think. Because they are a different type of problem. But I think I already got the stuff that I wanted to get from this run about these problems here. Just pretty much understanding what I have to focus on
Hey everyone,
and
welcome
what kind of
back.
things I need to pay attention to when I'm studying this. So that I understand what the issues in my thinking, the problems in the way that I'm thinking are, and what kind of questions I want to solve so that I know how to think about the problems next time.
Let's write some more neat code today. So today, let's solve longest common subsequence, a dynamic programming problem. And this is pretty much one of the most popular dynamic programming problems. So we are given two strings, text1 and text2, and we just want to return the length of the longest common subsequence between these two strings. And you might remember from my last video where we learned basically what a subsequence is. It's basically you take a string, right, like this string A, B, C, D, E, and you just, you choose a few characters from it while you maintain the order. So one subsequence from this string could be A, B, right? You take the first two characters from it. You can take any characters, you can choose to remove any characters, you can do whatever you want. And so we're looking for the longest common subsequence. So a subsequence that is in both of the strings. So in this example, we have two strings, right? A, B, C, D, E, and A, C, E. So what is the longest common subsequence between these? Well, when you take a look at the first string, you see that, hey, they both have an A, right? They both have an A in the first spot. So that's good. So now let's look at the second character, B and C. Well, this is a B, but the second string does not have a B. But the second string does have a C, and we also have a C over here. But the second string does not have a D, right? So we can't include the D from the first string, but then we see the last character is an E, the last character in the other string is also an E. So we get the longest common subsequence to just be the original second string, right? Ace, because ace can be found in the first string. All we have to do is remove a couple characters, right? Remove the B and remove the D, then we get a subsequence that matches the second string. So the length of the longest common subsequence is 3. So how can we solve this problem? Well, as I mentioned, dynamic programming is the most efficient way to solve this problem. But before we even get into the dynamic programming solution, which is going to be a two-dimensional dynamic programming solution, before we get into that, let's just notice one thing. So let's say these are our two strings, right? String 1 and string 2. Does it at least make sense to you that, okay, like we would want to start, let's say, at the beginning of both strings, right? Like we're looking for the longest common subsequence. It might just be that both of the strings are actually equal, right? That could be a possible way. So let's look at the first character in each string. And in this case, they match each other, right? They're the same character. So does it at least make sense to you that if both of the characters match each other, right? The first characters, that the longest common subsequence, then we can break it into a subproblem, right? Now, the new problem we're looking at is finding the longest common subsequence between the remainder of both strings, right? Plus 1, because we see that the first two characters are equal, right? That's where our 1 comes from, right? Because we know that the longest common subsequence is at least going to be 1 because we found a matching pair of characters, right? And then we have a subproblem, right? And you might know that that's what dynamic programming is all about, finding the subproblem. Now, what if this character was a B, right? And this is an A, so clearly they're not the same character. What would we do then? Well, we can't do what we just did. We can't add 1 and then find the longest common subsequence between the remainder of the two strings. We can't do that, but we can break it into a different subproblem. We can say, well, it's possible that the longest common subsequence could be between these two strings, right? Or it could be between this string and this string. So this is just a little bit of an explanation before I show you the actual dynamic programming solution, right? Basically, what we found out is that based on comparing the first two characters, whether they're equal or not equal, we can break up the problem into subproblems. subproblems and then solve those subproblems. So take a look what I just did. I took the two input strings, right, string 1 and string 2, and I wrote them in a different way, right? I said that this is a two-dimensional dynamic programming problem, and you might know that a grid, a 2D grid like this, is commonly used to solve these types of dynamic programming problems. So notice that for each character in both strings, there's a square, right, a position, a cell that we can put a value in. We're going to put a value in each of these cells. And so let's just start at the beginning like we did, right? So let's start at the first characters, right? What we're trying to do is for these strings, find the longest common subsequence between the entire strings, right? So what we're going to do is put that value right here. That's what's going to be the entire longest common subsequence. So we want to compute the value that goes here, but what you're going to find is to do that, we need to solve some subproblems and then, continue to do that and then work our way back up to this position. So what do we notice? Let's look at these two characters, right? They're equal, A and A, right? So, okay, so now we want to find the value that goes here. How can we find that value? Well, like I mentioned, right now we're trying to solve a subproblem. We want to find the longest common subsequence between these two substrings, right? We don't have to check these A's anymore because we know they match each other. So now I want to find this new subproblem, right? And so basically what I'm saying is I'm going to go here. I want to solve the subproblem that goes here. So now we're here, right? We're comparing this B with this C. We see that they're not equal this time, right? That means we're not going to be going diagonally. We're not going to look at this subproblem. We're going to look at a different subproblem. Since these characters do not equal each other, we have to check two different subproblems. It means that the longest common subsequence between these two substrings is going to be found in either of these two positions, right? So let's look at this position first. What this position tells us, we're trying to find the longest common subsequence between this string and this string, right? So basically we're not looking at this C anymore, right? And this position tells us that we're looking at the longest common subsequence between this string and this string. So basically when we remove this B, right? And just by looking at it, right, you can tell that these two strings are going to lead to a longest common subsequence of 1. Just by looking at it, right? Because you can see that this has one character, it's an E, it only matches this E, so that's going to be a 1. But when you look at this string and this string, right, corresponding to this position, we see that this has a CE, this has a CE, so this is going to end up being a 2. But let me actually solve the rest of it a little bit. So mainly looking at these two strings, right, in this position, we see that the C's match each other, right? So remember, when the characters match each other, the first characters of both strings match each other, that's when we go diagonally. And the reason we go diagonally is because then we know we can look at the remainder of both of the strings, right? We know that this C matches this C, so we want to look diagonally. We want to look at these two substrings. So what's the longest common substring between these two? Okay, so what are we going to do? Let's compare the first character, right? So D and E. So these characters are not equal. So remember what we do when the first characters are not equal. Then we can't go diagonally. So what do we decide to do? We go to the right and we go down and we take whatever the max of these two is and then put it in this value. That's what we're going to do. So first, let's check this right position. So what does this right position even mean? It means we're taking this substring and finding the longest common subsequence with this substring, but this is an empty string. So what's going to be in this cell? Remember, this is actually out of bounds anyway, right? So what default value are we going to give ourselves if we go out of bounds to the right? Clearly, the longest common subsequence between a string and an empty string like this is going to be 0, right? So really, what we're going to initialize is we're going to say every value in this column is going to be 0. Similarly, this is an empty substring. If we were trying to find the LCS, the longest common subsequence between this and an empty substring, we would also get 0. So what we're going to do is put a 0 in these positions, right? That's just how we're going to initialize our 2D matrix when we start the problem. Okay, so remember what we were doing. We were at this position, we were going right and we were going down, trying to find the maximum value. Well, clearly to the right, we get a 0, so that's not the max. So let's go down. Okay, now we're down. So what are we doing? We're finding the LCS between this substring and this substring. Well, they're the exact same, right? E matches E. Okay, great. And remember, when characters match each other, that's when we look diagonally, right? So we came down here, and now we're looking diagonally. Clearly, we get a 0 here, right? So 0 plus 1. The reason we're doing a plus 1 here is because we found matching characters. When characters match, we add 1 because clearly the LCS between these is going to at least be 1, right? At least one of these characters matches. So now I'm basically going to go here and then take us back along the path that we came from and then show you what the solution is. So we had a 1 here, right? And so from this position, we went down. So since we were going down, that means that this character and this character did not match each other. So what we're going to do is just take the 1 and put it up here, right? So there's going to be a 1 here because the LCS between these two is 1. But now we're going to go back over here diagonally, right? Diagonally means that this character matched this character, right? So we're going to take the value that we got up here, put it over here, and add 1 because remember, these match each other. So we're adding 1. That means we're going to end up putting a 2 in this position. And now we're going up, right? We're going up because that's where we came from. And remember, when you go up, that means the characters did not match each other. The C and the B don't match each other. So we're going to put a 2 here, right? We're just taking this 2 and putting it over here. And lastly, we're going back here. That's where we came from, right? Diagonally. That means the characters were matching each other. So we can add at least 1 character. So 2 plus 1, that's going to be 3. This is how we got the result, right? So we got a 3, meaning that the LCS between these two strings is 3, right? And that's what we learned from the problem explanation. So right, what we're going to do is return 3. That's our result. But you can see that the way I did it was basically intuitive, right? I used this picture and basically solved this problem by hand using a little intuition and stuff, right? But the way we're going to have to solve this with code is going to be brute force-ish, right? So it's dynamic programming, but what we're going to have to do is for every value in this cell, right? So we are going to initialize these zeros, right? But with this matrix, right, this 2D matrix, we want the value that goes up here, right? And to do that, we have to compute the value that goes here, that goes here, that goes here, and basically for all these, and then finally we'll be able to have the value that goes here, which is the result that we're going to return. And so basically what I'm saying is this is going to be a bottom-up dynamic programming solution, right? Bottom-up, meaning we're going to solve it in reverse order. We're going to first get every value, we're going to get the value that goes here, and then work our way up until we get to the result. And you might have noticed, see, I have an I that tells us the column, I have a J that tells us actually the column, and the I tells us what the row is. And so when we're working our way, starting at the bottom and working our way up, how are we going to determine what value goes in each cell? Basically what I went over earlier, right? So we're going to look at the characters, and if they match each other, what we're going to do is say 1 plus the value that's diagonal, right? And we know when we go out of bounds, there's a 0, right? There's an implicit 0 when we go out of bounds. And we're going to do that with every single cell, right? So when you look at these two, we get an E and a C, right? And when characters don't match each other, right? That's important. What we're going to do is we're going to look down, right? We see a 0 down here, and we're going to go right to the right side, and we see a 1 here on the right side. And what we're going to do is take the max of those two values, and we see that the max is, of course, 1, right? 1 is bigger than 0, and then we're going to put that max value in the cell. So that's really it. There are two choices, right? If the characters don't match each other, right, in this case, or if the characters do match each other in this case, right? That's basically how we're going to solve this problem. It'll make a little more sense when I show you the code. So remember, we're going to have a 2D grid. So I'm going to call that DP for dynamic programming. It's going to be a 2D grid. And what I'm initially going to do is set it to all zeros, right? So, and I'm just going to do a little bit of Python stuff. So list comprehension in Python. So we're going to go through every single value in the length of text2 plus 1, right? Plus 1, because we know that we need at least one more column to have all the zeros in it. And so remember, we're going to put a 0 for every value in that. So length plus 1. And we're going to have this row for every value in the length of string 1, so text 1 plus 1 as well, right? So we're basically, if you're not familiar with Python, this looks complicated, but basically we're getting a 2D grid of dimensions length 2 plus 1 times length string 1 plus 1 and initializing it to all zeros. And then we're just going to have a nested loop. And what we're going to do is iterate through this 2D grid in reverse order. So in Python, you can do it like this. And basically what I'm doing is starting at the bottom right of the matrix and then working our way up. So this is how you do it in Python, -1, and let's do the same thing for text 2. And so remember, so we're going through every cell in our 2D grid. And remember, there were two conditions. One condition is if the characters in both strings match each other. So if text 1 of I matches text 2 at position j, if they match each other, we're going to do something. If they don't match each other, we're going to do something different. So remember, if they do match each other, then what we can say is at this position, dp of I, j, because remember, we're trying to fill in every single cell. What we can do is then just simply take 1 plus the diagonal. How do we find the diagonal? Well, we can say I plus 1 and j plus 1, right? That gives us the diagonal. And remember, we're adding 1 to it because these characters match. That means we add a 1. And if they don't match, that's the else case, right? So we're doing something different here. We're going to put a different value for dp of ij. And in this case, what we're doing is we're finding the maximum of two values. What are the two values? The value to the right of this position. So we can say dp of I, j plus 1. We can say that's the right value, and the value below, the bottom value. So we can say I plus 1 and j for that, right? So we're finding the maximum of these two. We're not adding 1. We're not adding 1 because the characters did not match each other. But basically, literally, these are the two cases. We're just filling in a different value depending on what the case is. And that's it. So literally, with these two nested loops and with these two conditions, we're filling in the entire DP matrix. And so once that matrix is filled in, we know that the result is going to be at the top left of that matrix. So the DP, the matrix at index 0, 0. That's going to have our result. So all we have to do now is return the result. And clearly, you can see that the time complexity of this is the length of the strings multiplied by each other. So if the length of string 1 was n and the length of string 2 was m, we just multiply them together. So this would be the time complexity. That's also the memory complexity because we need extra memory for our 2D dynamic programming grid. Oops, I had just one little bug. I added one to the inside of that function, but I need to add one here. But other than that, you can see that the code does work, and it is.
Yeah, pretty similar to the previous one. And again, this part here is the one that I'm having the most difficult with understanding this grid here, the DP. I guess it makes an empty grid in the beginning. That's why I'm having issue. Is because the algorithm is replacing the values in the initial grid, and then he's returning the first one. But I don't understand why though. I think I'm gonna cut here, and I'm gonna come back really soon. I think it is a good time to cut because I just finished dynamic programming. And I think on these next few problems I'm gonna spend more time because they're different topics. So there might be things that are more interesting. So see you then.